I'm Saurav.Gupta. He's my colleague Elijah. We are two sales engineers from our UK office. And today we will talk about a new functionality within IRIS platform, which is based around a simple, I would say, a functionality which solves a difficult problem, but it does it in a simple way. And the idea is, how can we ingest data into IRIS as fast as we can? That's the problem that we are trying to solve here. And there are a couple of use cases that we are going to discuss, which basically we came across through our prospects and customers. And we'll talk about this new functionality, the first version of which is written in Java, and how it interacts with IRIS. We'll talk about that. But that doesn't mean it's only available in Java. It could be available in Python or any other language. So we'll talk about the challenges, the new functionality, the new component, and we'll talk about the two use cases, how we went about those two use cases. So the first use case is basically how, at the same time, when you're ingesting records at a high frequency, and we are talking here about million records per second, we could query at the same time at scale. The second use case was, again, a similar requirement where if we move from a database side to the integration side, where essentially it was a high-frequency message broking application, where essentially we need to receive messages at a high rate, enrich those messages, and send it to the downstream system. But again, the key thing over there is, again, the same thing. What we want to make sure that the client applications which are sending this data, we can persist the information within IRIS as queues as fast as we can, so that the time we take to process the message is pretty much the enrichment part of the messaging, which is dependent on any particular implementation. But the overhead of getting the data into IRIS and processing it is taken care of. Now, the challenges in high-speed ingestion and concurrent analytics is there have been different ways to solve these problems. I mean, a key thing is obviously is in-memory databases, but as we know all, they are very expensive to scale. And also, if things go wrong with them, then the time it takes for these high memory-based in-memory databases to come up is a big thing. The other ways many of the people try to solve this problem is to have two separate database services or databases, one they use for ingestion and one they use for analytics, which means that the database service which is ingesting data is separate from the database which is being used to query the same data. But the problem in that approach is, again, when you have two separate services, then essentially you have to worry about synchronization of data across those services, which is, again, a very expensive process. So essentially, and also the third problem is always that when you're querying the data beyond a certain scale, even to keep the indexes up to date, because the way you are querying data, probably you're aggregating data and all those kind of things, it becomes a complex problem. And people tend to have complex architectures for that. So let's see how we solve these two use cases with IRIS as a platform. So the component which we developed for this capability to get data into IRIS and persist the data into IRIS as fast as we can is called IRIS Persister. Gentleman over there, Dan Pascoe, who's part of our development team, is the guy who has built this component. And the whole idea is basically, how can we store objects on an IRIS server in using a multi-threaded loader? And that is the key thing. And obviously, when you're trying to store the data as fast as you can, it's not necessary you're going to receive the data in the form you're going to store the data. So you need a combination of how you could use a source schema and then put that into a target schema on the server. You need to map the data amongst themselves. And then finally, when you're consuming a data stream, you need to serialize it. So probably you're receiving a stream like a JSON structure and then store it into IRIS in a global module, which essentially has a table behind it. So essentially, that's what Persister does. And it also provides this mechanism where essentially indexing could be both immediate or deferred, which means for a certain use case, where essentially you want to first get data into IRIS as fast as you can, and you don't want even time spending in indexing because maybe you don't want to query at the same time, then you can even move the indexing to a further asynchronous process. So how does it work? So essentially, it's a multi-threaded loader, which basically has multiple threads written in Java. So when you start the persister, essentially what happens is it has one thread which basically establishes connection with the server to understand the target schema so that it can synchronize itself, that what is the data structure or the table definition that I need to insert the data into. Then it has separate threads which are acting as loaders and mappers, and then you write a consumer thread or a consumer program which is essentially trying to get data from the source applications. Now that consumer could be anything. It could be a consumer which is basically pulling off the data from a Kafka queue. It could be a consumer which is listening to a TCP IP port, could be anything. And we'll present two use cases that we did. In one case, we were getting data of the Kafka broker, and in other cases, we had a TCP IP implementation where we were just listening to a TCP IP port, and we were receiving messages from the client messages. So the data gets consumed by persister depending upon how you're going to get the data. So you write a consumer thread or a consumer Java class, which essentially gets the data. Then it serializes the data and pushes the data into buffers, and there are separate threads which are actually taking the data from those buffers and actually writing into the database, into the global structures directly, and behind that obviously is the class definition, which is your table definition. So in totality, this is what that component does, but let's look at the use case that we were trying to solve and how we did it. So this was let's say a large reputed data provider who came to us with a challenge. What they wanted to do is they were getting these streams of data essentially, and they wanted a Kafka broker which is going to give us the data. And they were storing all these real-time events into the database like bids, asks, dips, basically how the stock market trading happens, where there are quotes, there are bids, there are asks, and then the actual trades. And they wanted to store in the database, but at the same time, that same data needs to be queried in the front applications where actually people are looking at their portfolios in real time. So obviously, to solve this problem, we were looking at a scale of roughly 1 million inserts per second. That's what we were provided, and roughly 1,000 REST APIs per second. And these REST APIs were basically taking a ticker as an input and then going to the database, running a bunch of SQLs around it, and outputting it as JSON as the response to the client application. And when I say 1,000 REST APIs per second, the idea is that each REST API was equivalent to roughly 4 to 5 SQLs per REST API per symbol. And essentially, a REST API could also be a list of symbols where essentially you have 10 symbols, depending on what portfolio you have, that are coming together, and in real time, they're analyzing the data as the real-time data is being ingested for all the trades, depths, asks, and quotes. This is the architecture that we put in. As you know, like there's a IRIS capability of ECP has always been there. So that how do you solve this problem using IRIS? If you look at it, we always knew that if we have to do concurrent ingestion and analytics, then we always have our ECP architecture where our ECP nodes can be used as query nodes, where all the REST API traffic can be load balanced. The problem that we had to solve was, can we get 1 million inserts per second into IRIS? Because REST, we already had the infrastructure within IRIS for doing concurrent transaction and analytics. So this is the architecture that we put in, where essentially the persister had a consumer thread which was actually pulling off the events from a Kafka queue, storing it in the database, and then we had 3 ECP nodes connected to the database, and we created 3 REST clients to mimic the traffic, which were like JMeter nodes, which is a harness to send REST traffic, sending to it to a load balancer, and then finally load balancing that traffic across ECP nodes and doing the queries in real time. So concurrent transaction and analytics architecture, this is what it looks like. We did this whole proposition, I would say, in AWS. And essentially, we had, let's say, for the purpose of this, we had 3 JMeter nodes which were acting as the REST clients because we had to generate that much of query traffic, around thousands of REST APIs per second. We had 3 query nodes, which are nothing but our ECP nodes, and we had a database node. And the data that we were trying to consume was a sample data that we received for a day, where each stream of data was around 500 bytes. We had close to 140,000 symbols. And then we had a managed, I would say, Kafka cluster, where we loaded the data from S3 buckets into that. And then our Persister consumer thread was actually pulling off those events from the Kafka cluster. So the architecture is same. How we implemented was that we had a consumer, and multiple threads of these consumers were basically pulling off the topics from a Kafka broker. And we had these multiple threads for different global structures in a schema, or different tables in a schema, which were actually where the records were being serialized and written into their buffers. And finally, there was another thread which was reading of these buffers and writing off to the database. How did we do, actually? So what was the infrastructure that was needed? So on the database side, we had 32 cores. Again, memory, it's just the way the cloud is. Typically, when you provision a 32-core server in AWS, it gives you that much of memory. Not that we needed that much of memory. But typically, for this particular workload, I would say of concurrent transaction and analytics, we were using 32 cores in terms of CPU on the database node. And there were 3 ECP nodes of 4 core each that we were using. And we were looking at around, on the database node as well as on the query node, we were roughly looking at 50 to 60% of the CPU. And we benchmarked basically to see that, okay, in each REST API, if there were 10 symbols per REST API, what was the mean response time, which was around 400 milliseconds. Then, average response time was 16, and maximum was 285. And essentially, with 30 symbols, if you see, there is a little bit deterioration, but still, if you look at it, we were scaling quite well, whether it was 10 symbols or 30 symbols. And if you put everything into perspective, essentially to achieve something like this, we were using 12 cores on the ECP node and 32 cores on the database node, which was around 44 cores. And I think so the prospect told us that if you were to build this in a native cloud paradigm, and if you were to do this in AWS, they were taking more than around 150 cores to achieve this kind of scale of concurrent transaction and analytics of around 1,000 inserts, 1 million inserts per second and 1,000 REST APIs per second. Use case 2, I'll hand it over to my colleague, Elijah, to talk about it.
Thanks, Saurav. So this use case is sort of differs quite significantly from what Saurav just presented. So Sarav's presentation is more about polling Kafka topics and then surfacing the results of those through REST APIs, which you can query simultaneously. The idea here is that instead we're implementing a message broker. And the idea of a message broker is you might have some sort of upstream system, which is providing various types of trading data, and you need to route that data to the correct place. It's not so much about surfacing it as analytics, but more about routing. So actually, it's a pretty good use case for interoperability, because here, instead of just simply persisting it to the database and exposing those results in a REST API, instead, we want to actually route those through business components. And so that provides a slightly different challenge. Here's an overview of what we are working with. So we said that this is a message broker between a trade management system and a post-trade management system. And so if anyone here is familiar with fixed protocols at all, you'll know that quite often these messages will be submitted over TCP. So that's actually why we configured a sort of a TCP service, if you like, or a TCP server, rather than using our typical Kafka consumer. So we're still building a consumer in a sense of the word, but it's not going to be a Kafka consumer. We're still just going to be polling something different. So these will be queues that are generated from the TCP server that we've written. And then it's much the same process. So we receive JSON events from the TCP clients. That's really identical to how we're working with the Kafka broker. And then we serialize and store the JSON into IRIS persistent objects. And so, again, we need to retrieve the correct message schema. So that's the target schema of the class that we want to persist these into. And that's effectively the target structure that we want to serialize these into. And then there are a few other components going on here. So we've got a very abstract diagram at the bottom. We've got a more specific one in a minute, don't worry. But the general workflow for these is you can have multiple TCP clients connecting directly to the Java component. So this Java component isn't just Persister. We've also built the TCP server as well within the same package. And then it goes through this enrichment logic, which is just in the form of a business process. And then you can submit it into a business operation much the same way as you always would. And then it can end up in a downstream system. So there's a lot to unpack here, so don't worry. I probably should have added a few animations to sort of unveil it slowly, but we'll work it out together. So for now, let's just focus on the left-hand side of the screen. So we're looking at the source system at the top, which I've given a very generic icon, and we're looking at the Java program itself, just here. Don't worry about IRIS for now. There's a lot going on there. The left-hand side is fairly straightforward. We start with the source system. So in this case, we actually... Yeah? Is that better? Yeah. OK. So in this case, we have our source system, which we replicated with, well, we built with just a TCP sampler. So you could actually use JMeter, which is what we used when creating HTTP requests for the previous use case, or you can actually write it in object script, which is something we experimented with as well, so to generate those messages on the same IRIS server, but those are just details, really. It can be any source system that you want. And within the Java program itself, this TCP server exposes a particular TCP port. So we're working on a single port for this. The idea is multiple clients can connect. And then, I don't know if anyone here is familiar with the NetE framework. I'm not going to pretend that I'm particularly familiar. This wasn't something I built personally, but once it arrives at the server, there's a channel pipeline. This is the terminology for it, which basically contains various logic for decoding, encoding, exception handling. The idea is you can filter the bad messages out and keep the good ones. Yeah. So the good messages end up in the inbound queue, as we call it, which is something that Persister is aware of. When you define a Persister instance, you define it with these inbound queues, and you define it with a message schema, which is sort of what you're seeing in that dotted arrow there. You can, for those of you that went to Stefan's presentation, you'll know that there are various ways that you can actually use a schema for your messages. In this case, we decided to pull them directly from the IRIS server, so I've got a very generically named record.cls. That's our target persistent class. We are pulling the schema from that class for the Persister instance. That's what it's using as its target data structure. Cool. So now they're in the inbound queue. Persister has several threads running that will start serializing within those inbound queues. The idea is you can have multiple Persister instances. So in fact, if I quickly go back to the previous use case, you'll see there is not one Persister, there are in fact 3. And in fact, in this, there are actually 7 or 8, but I chose to put 3 on this diagram. The idea is each Persister instance corresponds to a schema. So that's what's going on here. We're not going to have a single Persister instance serializing messages to a bunch of different schemas. So it's a distinction, I think, that's worth making, certainly in this iteration. So if I go back, there we go. And once they're serialized, they're mapped. They're mapped to the schema, and those mapped records are then added to a buffer. And then we've got a separate thread which is running. And once the buffer is filled, the contents of the buffer are then written to the IRIS database. So far, that's pretty similar to the previous use case. What happens next is a little bit interesting, because the question is, how do you then bring these records into the interoperability layer? How do you bring that into your production? So far, we've just got a bunch of records sitting in a table. We haven't sent them through a business service. We haven't done anything strange. It's just standard IRIS. So what we devised was this thing called a notification service. It's the thing with the big exclamation mark on it. And what that's doing is it's actually checking the number of records in that table. So we've told that service which table to look at. So in this case, it's going to be record.cls. And when it detects that there are new records, so it remembers how many there were previously, just using a single global, it then just sends a blank asynchronous request to a business process, the enrichment process with the cogs, and it says, wake up, there are new records here. That business process then performs a %openID on all the new records that are in there. Again, it knows the old global, it can work out the new global pretty easily, and that's that. So you can open each of those records. And the benefit of this is there's no queuing between the business service and the business process. Here, you are directly opening the records in your business process. You can do whatever you want with them. There are no limitations there. And we found that if you simply tried to submit these records over the inbuilt TCP inbound adapter, inbound service, the performance is so much worse, you wouldn't believe. But when we did this, I think we found we got about 25 to 30,000 messages per second into the business process. So these are messages being opened every second, which is pretty impressive, I'd say. Yes, that's a great question, actually. So we experimented with increasing the pool size of the business process. So, if you just have pool size 1, it's pretty straightforward. If you have pool size 10, that's also okay. The question is, though, do you want first in, first out? So when it comes to trying to sequence these, you'd also want to be careful about which globals you're locking, but otherwise, it's doable. So we experimented a bit with trying to sequence the messages as they come out of the business process. So what we found ultimately is that our client didn't necessarily need that, but it was fun to work it out anyway. And I say fun, it was a bit of effort, to be honest. But we sort of reused a slightly older project, which is a separate business process, which we refer to as Sequence Manager. The idea is every time you successfully enrich or process or whatever one of these messages inside the BP, you then send all of these messages to a single business process, which then works on a certain type of ID. So you could theoretically work by a timestamp. You could use whatever you want. Using an integer ID is probably a better idea, but so we played around with that a little bit. And once that works out, then there's really no limitation for what you can do next. So the concept of a message broker is it then needs to be sent to other downstream systems. It then needs to be enriched in various ways. This way, you have complete access within the interoperability layer. And there are a few other challenges that you need to focus on. For example, if you wanted to send every single one of those messages from the business process to a business operation, you're still going to get the queuing issue. So then you need to devise a different way. Do you want to persist it back? Do you want to have a different notification service? Ideally, with a system like this, you're not sending everything everywhere. You're going to be sending a few messages that you need to the right place, and that way you don't have the sort of the performance overhead that you would expect from 30,000 messages per second flowing through a single component. But otherwise, it's a pretty straightforward solution, and it worked very well for the client's needs. I think the other thing I'd say is you don't necessarily have to, for all of these projects, we place the Java application on the same host as IRIS. You don't necessarily have to do that. Network latency was a bit of an issue for a lot of these projects, as you might imagine, particularly the first one, when you're dealing with thousands of HTTP requests per second. You've got different EC2 instances that are communicating with each other. We've had a bit of a nightmare with various cloud configurations. So when you're actually making the connection between your Java application and IRIS, you don't have to define it as localhost. You can make these connections with the same flexibility that you'd expect from a typical connection object that you'd work with, with any IRIS Java driver. And I'd say that's pretty much it for this use case. So as I said, we got to about 30,000 messages per second on a single port here. We have ambitions to scale this up further. No, please.
So when you move from the BP to the BO, were you using the standard queuing there, or were you sending each message individually, or were you batching them in there?
Yeah, so in this case, our idea was we would be sending a much smaller proportion of those messages to the BO. So we said, yeah, just make a standard asynchronous request. Yeah, exactly. And that way it's still queuing, you still have access to all the...
And also there is the same probability that if we feel that queuing is again limiting us, then the same notification mechanism could work from the BP to the BO level.
No question. Is the notification service part of IRIS now, or is that something you guys do?
This was custom.
No, I mean, this is just looking at a global and seeing if there are, it keeps the last processed ID. Yeah. I mean, what we found was that, I would say, and in fact, it was a revelation for me personally, I would say, is that the amount of overhead we have when we do something like send request sync or async from a business service to process is quite a big limiting factor.
The queue manager.
Yeah, exactly. And also that everything over there is then implicitly issues a sync commit, which means again you're going back to the disk. So in this particular case, if you look at it, Persister has already done the magic in terms of getting into IRIS, which are nothing but persistent objects, but they're behaving as queues in this kind of a scenario. And we are just in the business process, all we are doing is the idea of service over here is only to let the business process know, wake up, you need to do something, as opposed to sending the message or anything like that, because the message is already persisted. And the business process is just then opening that record because it knows which message it is looking for and does the entire enrichment. And in our experiments, I would say, when we were doing these 30,000 messages per second, the reality was that the rate at which we were getting it, the rate at which it was being received at the process. So we had pretty much made any overhead of the service taken away. And now we had to worry about the process, but which we can obviously have multiple ways to skin the cat, because at the process level, you can have multiple pool sizes, or like we suggested that if it is critical first in, first out, then we also experimented with the idea that we multi-process, because process has the most, let's say, processing built into it, because all their validations, transformations, everything is in the process layer. So if we multi-process it and then have just one component, which is again just doing first in, first out, and we didn't go further, but Dan did let us know that when he's actually getting the data from Persister into the queue, he could assign IDs at that time, which gives us the order in which we receive it. So we could always resequence it in the order which we receive and send it further to the downstream system. So in my opinion, I think so once you are there are multiple ways to actually solve the problem.
Do you send everything from, I mean, because you have one persistor per schema, right? Does every persistor have its own process? Or do you...
So there are multiple instances of a persistor, right, and these multiple instances are nothing but each instance corresponds to one table within that schema. So in our schema, let's say if we had 7 tables which we were trying to consume the same stream, so let's say in our case, we had these streams of messages coming, and it had one property within it called message type. Based on the message type, it was to be persisted into 7 different tables. So we had 7 instances of persister, a single persister on the server, but 7 instances of that persister class, which maps each of that serialized thread, serialized message to that particular class structure, which eventually gets. And the other part is, if you look at it, what you see is over down where this, let's say filled buffers are written into the IRIS, those are just writing buffers. They don't care whether it is this persister instance or this persister instance. The buffers are being written by that writer thread, irrespective of the schema, let's say.
So let's just say theoretically you had way more trades than asks or bids and you were overloading the persister. Could you actually set up a second trade persister or a third?
Well, actually, we've got some configurations in terms of the number of threads you want to assign to certain things. So theoretically, what you could do, I mean, I'll quickly, how many of you have worked with production extensions? Is that none? Okay. Well, you're going to learn something else today. So if I just quickly, so the one arrow I didn't explain, it says PEX business service up there. The idea here is actually you can manage a Java application from IRIS. You can also do it with some Python applications, and you can do it with .NET, as long as you build it out in the right way. So we have certain drivers that you can import, and you can use those to effectively define this as a business service, which is what we did here. And part of that means you can define settings from the production. So theoretically, you could have multiple persisters if you wanted, and that way you could have complete sort of decoupling of how many threads are in each one, and you can have one port for trades, one port for asks, whatever you want. In this case, one was fine for everything. But yeah, you're absolutely right. You can have a lot of flexibility over how you deploy this, and you can configure it from the production, which is pretty cool.
And the whole idea in this case was that if you look at it, when you start the production, the PEX business service is actually calling the persister component. And the persister component has its TCP/IP implementation. That TCP/IP implementation is not in the PEX service. The PEX service only gives you a configuration what TCP/IP port you want to open to which the client can send it, which then gets passed on to the actual persister, which has this TCP/IP socket implementation, and it opens that port for it. So if you look at it, almost like the business service in this case is almost like a proxy thing, which is just passing on certain settings. And the whole idea is that we had to integrate the calling of persister into the production framework so that when somebody starts or stops the production, the persister is opening that TCP/IP port and ready to receive messages. And similarly, if somebody stops the production, it no longer is receiving the messages. That would be great.
That's very surprising. Yeah, I mean, this is ultimately designed around getting as much into IRIS as you possibly can. And yeah, I'm interested to know what those healthcare use cases.
So we do the VA referral management. I'm CCRA, and we process 3 or 4 million HL7 messages a day.
Sure. Coming
from all the vistas and servers coming in through a single HL7 pipe. And we overloaded the systems. What we ended up having to do was be cute, and we manually route and have 10 listeners because one HL7 can't keep up because we're overloading the queue manager. So we have the exact same scenario you're describing here, except we feed the HL7 into your persister and move it into a record and then pick it up in the process.
And also, I think so one of the challenges with this approach, which we still have to address is, so if you look at it in this approach, you no longer have the visual trace between the business service to the process. But then the question is, and I think so that's a valid question, which Dan has always said, and even Alex, that if you're doing 30,000 messages per second, in any case, you will have to come some other way of identifying your messages. You are not going to go into message viewer and try to search them. Yeah, exactly. So essentially, for a use case like this, there is some other tooling needed, but that would be so case specific, how they want to actually, whether that's an audit table which shows the trail of the message, or there is some UI where they key in a GUID or something like that, which then brings it from the database. But the reality is, and in some way, as much as powerful feature visual trace is, it forces you to send objects from one component to another, and that's what is an expensive process if you look at it. Yes, please.
Can you go to the Kafka?
Absolutely.
So there was a question earlier about the, for example, if one persister were to have higher ingestion than another, and you said how you can configure the number of credits. I almost wish that was more dynamic, because on any given day, it's not necessary that one persistor is going to see that, but if you configure it beforehand, it's almost as if you have to understand, you have to understand the nature of the data that's coming in prior.
Yeah. So that's a very valid point, and I don't see why this couldn't theoretically be containerized, and you could have this working in a cluster where you can scale up and scale down. What I would assume, though, is that you'd actually want to take this Java application, containerize that, and so you'd have some. So in this case, we've got several persisters defined in the same application. You could have one persistor defined in each application. I mean, you could have an identical container for each one. Each container, the only real difference between them is what schema they're pulling from IRIS, right? So you can bring each of these generic containers up. They pull whatever schema they need as they instantiate this persistor object. That's totally fine. And if you need 18 of them, if you need 18, you might have to work out how to use the consumers properly. But if you wanted to have 18 different persisters, theoretically, that's fine. Although you may need to just be careful about how some things are being managed. But
that's something we need to look into, honestly. I mean, that's something, ideally, let's say, it should not be that we change the deployment pattern to achieve a certain scale. It should be possible to it. And I think so that's in our list of to-do things, let's say, which is again probably, as I said, this was more driven by the use case that we had to solve, and we solved it, and that's it as far as we were concerned. But yeah, even I think so. I mean, we had discussions with Dan in the other case of message broker. Is there some magic which could be done where you could have almost 10 mechanisms of like this, of a persister still writing to the same table? That would be an interesting proposition, I would say. But yeah, these were the use cases that we could solve by using the same component, but in two completely different contexts, if you look at it.
we should also mention the availability of Persister as well for anyone that is feeling adventurous. And, there we go.
So the idea is to make Persister available as a separate component through the artifact repository, as opposed, because it is a standalone Java component which could work with any IRIS instance. So, but the plumbing needed for using Persister is already there in IRIS 2022.
So you said you could distribute these, which means it's TCP between Java and IRIS. It's not an in-memory connection. How's the data being passed? You're writing that buffer, but is it over TCP or are you doing something in memory?
It's all setting up complicated. The specific case, I think we use TCP.
Yes.
So just for the recording, this is all built on JDBC. In this particular case, we use TCP. Yeah, thanks for clarifying.
It's usually JDBC product. It's not this JDBC call.
Okay. Yeah.
For those of you familiar, this is based on XCP technology. Next generation XCP.
Cool. Thank you. Well, if there are no other questions, then thank you very much. And,
Thank you.